Welcome back to our Pre-AP Chemistry Unit 7 notes. We have already gone through like the introduction and topics 1 and 2. So if those are the ones you need to make up, then please go to an earlier video, not this one. We're starting this video with topic 3. We're going to discuss strength of the bonds. How do we tell how strong the bonds are? What are the characteristics that come from these bonds? Okay. So again, this is a new row across your 4-column notes page. New row, strength of the bonds, and then here's ionic bonding, the column to the left of the center line. So in general, ionic bonds are very strong. Okay, the actual strength of the bond, how strong it is measured in the amount of energy it takes to take apart the crystal lattice. So we call that the lattice energy. That is the energy it would require to separate those cations and anions that are in the crystal lattice and turn them into single gaseous atoms. So what you need to remember is the higher the lattice energy, the stronger that ionic bond was. And if it's a low lattice energy, then the bond was weak, at least in comparison. That's as far as you need to go with that. Okay, so next column, covalent. Covalent bonds in general are really not very strong, not compared to ionic. Ionic bonds tend to be really strong, mostly because ionic bonds are really strong because you have gazillions of cations and gazillions of anions all acting like little magnets sticking together. So it's sheer numbers going on. With a covalent bond, they're not nearly as strong on the most part. And we're going to measure the strength of a covalent bond with that bond energy that I discussed earlier. That's the energy you have to put in to turn the bonded atoms into separate atoms. Remember, we had a graph that kind of did this, where up here at this level was having single atoms, and down here at this energy level was having bonded atoms. And so the energy it takes to lift it up that potential energy hill, if you will, call it a hill, that is the bond energy. All right. So the higher the bond energy, the stronger that covalent bond was. So if it's some other thing that's very weakly held, another type of covalent that's weakly held, then maybe you have something like that, where the hill is rather shallow. If it's a noble gas, we already mentioned this, I'll mention it again. With a noble gas, like, they practically have no divot at all. It's just a little tiny itty bitty bump, meaning that even if they were to bond, it would take so little energy that the environment provides it to break the bond. And so the bond, even if it were to form for an instant, would not last, which is one of the reasons that the noble gases are so unreactive. The bond energy given off is there's no potential energy decrease that is accompanied with bonding for those noble gases. Okay, so bond energy is how we determine the strength of covalent bond. The greater the number of the bond energy, the more strong the bond was. It's that easy. Okay, now we're still in the covalent column. I want to introduce the idea of a bond length, because this is a concept I expect you to know. Bond length, how long the bond is, okay? Measured, that is, from the nuclei to the nuclei of bonded atoms. So here we have some diatomic halogens going on here, all right? And it's how long the bond is. And so bond length will tell you the length of the bond from nuclei to nuclei. But here's the part to catch, okay? For instance, fluorine, which is one of the smallest atoms there is, notice the bond length is between two fluorines is really small compared to, in the same family even, iodine, which has it's a very large atom, especially compared to fluorine, but just in general it is a very large atom. Well, because of all the electrons in the electrons cloud repelling each other on both sides, there's not the ability of those nuclei to get really close to each other. It just gets crowded in between, and they can't get all that close. So what's going to happen is we have a longer bond length. So this should not be a tough question. What seems easier to break? A small bond length or a large bond length? What would be easier to break? A small stick or a longer stick? And if you think back to childhood days when hopefully you went around breaking sticks or whatever, a long stick means you could put your knee up in the middle and get some leverage and break that. And that's exactly what can happen. Now, there's no one putting their knee in between a bond, but these iodine atoms being farther apart can vibrate more strongly, as if that bond was a spring, back and forth, and get enough momentum, enough force to break that bond. Whereas with a tiny bond, there's not going to be much movement going on there. You see little bitty tiny kind of movements, and so it's not as easy to break that bond. So with a covalent radius being smaller, that is the bond length, okay, being smaller, a smaller bond length is harder to break. What's that mean about the bond energy? Bond energy is going to be big. And when the bond length is big, the bond energy is going to be small. So you absolutely need to picture in your head and understand and know why and be able to tell me that if the bond energy is high, that meant the bond length was low. Or if the bond length is high, that means the bond energy will be low, that sort of thing. Easy to break a longer bond, harder to break a shorter bond. So get that firmly put in with bond energy in your head and all held together so that you remember that. Okay, we're ready for our last column, the far right column of your notes with metallic bonding. Metallic bonding, there's just no generality. There's no way to generalize because it varies depending on the metals involved. And we have a lot of metals on the periodic table. So depending on the metals involved, it could be very strong, it could be very weak. But we do have a way to measure. We're going to measure it with this thing called a heat of vaporization. That is the energy required to separate the bonded atoms into gaseous or vaporous atoms. Okay, so I take a solid metal, okay, something like this going on, all nice and neatly bonded in that sea of electrons model. And it's, let's say in this case, it's like two elements. So some elements are my yellow element here, and some elements are the red element going on there. Okay. The energy it takes to separate that all into individual atoms floating around of yellow and red. Oh, that was supposed to be red. That's weird. Let's try again. Okay. So to have these, to go from that to that, that's heat of vaporization. Okay. And this is what you need to know about. The higher the heat of vaporization, the stronger the metallic bond. Now, I really hope you've caught that. We have three ways of measuring the strength of a bond. For ionic, it was the lattice energy, and the higher the lattice energy, the stronger the bond. For covalent, it was bond energy. The higher the bond energy, the stronger the bond, also the shorter. For metallic bonds, whether they're strong or weak, hard to generalize, but the heat of vaporization, if it's high, we have a stronger bond. So there's a way to measure each type of bonding, a way to put an actual numerical value. You could go to the back of some textbooks, usually college ones, and look up these heats of vaporization and lattice energy numbers and compare. We don't need to do that for our class, but you do need to understand what it means to have a higher heat of vaporization or a lower heat of vaporization. What's that mean to the strength of the bond? Okay, so draw a line across all your four columns, and here's topic 4. So put that in the far left column. We're going to talk about properties of the compound. Now that you know what makes up the compounds and how strong or weak the bonds are, what can we expect from the properties, just the general characteristics? What is it going to be like? A lot of these should be familiar with you. So we're now in the ionic bonding column. That is the one to the left of the center line. And as I've said before, the forces holding the ions in an ionic bond together, because there's so many ions, always gazillions of each charge held together, very, very strong. So what we tend to see is we tend to see high melting points. The heat it takes to melt it is usually relatively high. Okay, for instance, water, the heat needed to melt ice into liquid water is 0 degrees Celsius. Well, what if you want to, I don't know, melt gallium? The heat needed to melt gallium, which is one of the lowest melting metals, is about 95 degrees Fahrenheit, or I would call that like 36 degrees Celsius. So it's already above that of water. And if you thought about, we boil water in pans made of metals. So it takes a lot of energy to melt ionic bonds. So that should indicate they're very well held together. It takes lots of energy to wiggle them enough to where they're going to break apart and melt. If it's a lot of energy, because they're strong bonds, to melt it, it's even more energy to boil it. Okay. And then we have poor conductors. Ionic compounds are poor conductors as solid. The electrons are stuck. They can't move. They've been captured. Remember that transfer? They've left one ion, they've joined another, the atoms are ions, they're all stuck together. So they're poor conductors of electricity as solids. But check this out. When we do finally, if we put in enough energy to melt them, have you ever tried to melt salt in a pan on your stove? You probably never have, because you'd be bored. It's going to sit there for a long, long time not doing anything, and maybe eventually your stove would get hot enough that it could melt it. Well, if it really can melt it and you needed it to, it would conduct electricity. So they conduct electricity when they're liquids, and they'll conduct electricity when they're dissolved. That is because those ions are free to move about. So my little sodium ion and its big chlorine ion, sodium positive, chlorine negative, when those are melted or dissolved, they separate. Now they're still ions. This one still has one more electron than this one. But now they're separate, and so the electrons can kind of move from one to the other throughout the melted state or the dissolved state. We call that electrolytes. And if that seems like a familiar vocabulary word, well, you probably have heard it in commercials before with people talking about things that, are electrolytes that you can drink. We will definitely get back to the idea of electrolytes later in the year. All you need to know is that's the vocabulary for it. When the salt has ions that are free to move about, that's an electrolyte. Okay, and from these ions, electrons, which is electricity, can kind of like hop, skip, jump from one to the other, as those are now free to move. Because the bonds are still really, really, really strong as a solid, we're going to see ionic compounds are hard, very, very difficult. I can make powdered sugar pretty easily, just like pull out a rolling pin and start kind of rolling over sugar, and it's going to become powder without too much force. Maybe I'll lean on the counter a little as I do it, but that's about it. For a salt, I would be like sitting there forever. I'd be damaging my countertop or maybe my rolling pin, not crushing it, because it's really, really hard because of those strong bonds. But if we do apply enough force, you need to understand this, they are brittle. When you do apply enough force, they do not bend, they break, they shatter, they crush apart. They don't smoothly transition to some other, it's nothing smooth or anything. It just falls apart. It's brittle. Okay, so now we're in the covalent column, so the one directly to the right of the center line. Covalent molecules compared to ionic molecules are not very strongly held together. So what are we going to notice? Lower melting points, like solid water turning to liquid water at 0 degrees Celsius. Relatively low melting point. A lot of covalent molecules are actually even lower than water. Okay, if they have low melting points, they're going to have relatively low boiling points. The boiling point of a lot of our hydrocarbons is even below 100 degrees. Butane, like in a little lighter that you would use to start a Bunsen burner. It's stored as liquid in there, but the moment I press the little, I don't know what you call it, little plastic foot on the top, okay, to release the gas, it actually is allowing some of that liquid to boil. So it's like boiling in my hand because there's enough heat just in the environment to turn it to a gas. So low melting points, low boiling points, because they're not very strongly held together. They're always poor conductors, whether they're solid, liquid, or dissolved. They might dissolve. That's perfectly a good choice. It's possible they could dissolve. But even if they did dissolve, they're not ever going to conduct electricity or heat really well. They're not as hard as ionic compounds. They often are brittle. If they are in solid form and you hit them, they're probably going to shatter. Okay, so now we're on the far right column with the under metallic bonding. And the forces holding metals together, again, we can't really generalize. It really greatly depends on what metals are involved in the bonding. Some metals will have really strong bonds, others not so much. So we will get a whole range from low to high melting points, or low to high melting temperatures. We'd have some low to high boiling points then. Now if it's a high melting point, I would expect a high boiling point because those two would like match together. And if it's a low melting point, then it's a low boiling point because those two would match together. Metals are good conductors of heat and electricity as solids. You don't have to do anything to them. I remember when I taught IPC, we would do the is it a metal lab, but one of the things we would do is test if it can conduct electricity. So we weren't even just looking, does it look shiny, does it feel solid, does it feel cold, is it hard, that sort of thing. We even tested, will it conduct electricity? They're very good conductors as a solid. Okay, so why is that? Because those electrons are delocalized. There's that sea of electrons. Electricity is moving electrons, and a sea of electrons is a perfect place for electrons to just move around super easy, which is one of the reasons we like to use metals for wire. Now, metals and metallic bonding can be soft, that is relatively soft, and they could be relatively hard. Some metals are famous for how soft they are, like gold. Pure gold is so soft. If you were to actually wear pure gold jewelry, the moment you like bumped it against a wall or a desk or something, it would like fall apart on you. So no one ever wears pure gold jewelry because it's just foolish. It'd be a waste of money. But others are really, really hard, like titanium is very, very famous for being a very hard metal. So it depends on the metals involved. Regardless of whether they're soft or hard, if you do hit them hard enough, they will bend, not break. They're malleable. Think mallet, like the old wooden hammer. Hit it with a mallet and it will bend. It will not break. It's not brittle. It's malleable. They're also ductile. That means they can be stretched into wire, which is another good reason that we like to use metals for wire. They're good conductors, and most metals are ductile. And we really like metals like copper and gold because they're very well stretched into wire and they conduct really, really, really well. Gold is one of the best conductors of electricity we have, but no one's going to pay to put gold wires in their house when you're going to like cover it up with insulation and never see the gold. That would be foolish. And most circuits in a house don't need really, really good conductors. They need just good enough anyway. There's usually enough electricity coming into your house to compensate for the loss. So, ductile, stretched into wire, malleable. They can be hit with a hammer and they will bend, not break. Now, sure, there might be a point in which some metals break, but they will start bending first. Again, it's hard to generalize, but they would have, some have low tensile strength, some have a very high tensile strength, which is like why we build buildings out of steel. We can make an entire building's outside look like glass because it is like pretty much all glass on the outside. And it's like, what's holding up all that glass for that 100-story building? Well, it's a steel inside because of the high tensile strength. It can be pulled and resist breaking when it's pulled apart like that. And then we're used to metals being lustrous. The shininess of metals comes exactly from that sea of electrons, those delocalized electrons. They are the reason that it's lustrous. And it's even a little interesting to think it is those delocalized electrons, specifically in copper and gold, that give it the characteristically yellowish color, unlike the grayish silver color of everything, all the other metals. It is just that particular location in the periodic table has just the right electron arrangements for the color to be different. So very shiny because lots of electrons that are very easy to move and can reflect. It'll absorb light and then re-emit it back into your eyes, and we see that as a shine to the metal. All right, so finally draw another line across, and we're ready for our fifth and final topic. It is a big one, though. There's a lot of things to discuss here. I call it special topics. This is kind of just like where anything else that hasn't fit into an earlier category is going to be here. But these are still very important things you need to know, which is why we're spending the time to look at them. So in the far left column, you should have written special topics. And then in the next to the far left column, and the one immediately to the left, the center line, let's talk ionic bonding. I want to be sure you catch vocabulary of this thing called a polyatomic ion. Some older chemists refer to it as a radical. The AP chemistry teacher I took over for when she retired for the second time, she called them radicals all the time, and that was just the word for it back then. So just know we're now kind of switching to the idea of polyatomic ion, but of course you might hear some old chemists call it radical. It is a overall charged group of covalently bonded atoms. So even though they're all stuck together inside with covalent bonds, overall they have a charge, so they will then bond ionically. Now the charge of the polyatomic ion results from either too many electrons than normal or too few electrons than normal. And so once it's done, once you have a polyatomic ion, it will form ionic bonds with other things that form ionic bonds. So we know sodium will form an ionic bond because it's a cation. Well, we could bring in something like, I don't know, bicarbonate. Okay. Let's see, 3, 4, 5, all 5 atoms in bicarbonate here are covalently bonded together. But overall, all 5 atoms has 1 electron more than those individual elements would have. So they are overall negative, and here's overall positive. And look, opposites attract. They're going to form an ionic bond if they get close together. And again, they will form the right ratio of sodium and whatever, okay, to form a neutral or zero charged compound. So if it was sodium forming with carbonate, which is -2 charge, it would actually take 2 sodiums for every 1 carbonate. And nature, again, will work that out because it has a gazillion of sodium and a gazillion of carbonate every time it has any of those, because the atoms are just that tiny. Even the smallest speck of sodium you could imagine is way more atoms than you would ever be able to count. Okay, so now we're ready for covalent bonding, and this is going to be a big one. And we're in the column that's immediately to the right of the center line on your paper. We've covalent bonding, ionic bonding, metallic bonding. Those are forces inside molecules. Okay, those were intramolecular forces. We're now going to switch to what's going to hold one molecule to another, and that's called an intermolecular force. Inter meaning between, molecular for molecule. So I have a molecule of something going on over here, and I have a molecule of something going on over here. And all the atoms that are bonded inside there together, whatever that may be, that covalent bonding, or ionic bonding, or metallic bonding, that's an intramolecular force inside. Is it possible for this molecule to attract and form a bond with that molecule? That's an intermolecular force, a force in between the molecules, intermolecular force. Very much so, same reason we use inter for internet, a network between computers. When I'm on the internet at home, my computer's connected to other computers or servers all over the world to give me the information I want and check my email and Facebook status and all that, crazy stuff like that we can do. That's the intermolecular, that's the internet. Also in my home, though, I have an intranet. My TV is connected to my computer, connected to my DVD player, connected to my stereo. It's all connected in an intranet that is inside my house. And so I could actually, like, from my TV, pull up files to play videos or music from my computer, or I could, like, pull it up on my phone and send it to my DVD player to show on the TV, that sort of thing. So be very aware of what these prefixes mean. They should not be new, but we're going to talk now. So far, in these notes, we've been talking about intramolecular forces. We're about to talk about intermolecular forces. Okay, so we're in the covalent bonding column still. There's 3 types of intermolecular forces, and we're in that covalent bonding column still. The first is hydrogen bonding. Really tough question. What's needed for hydrogen bonding? Well, everyone says, well, I need hydrogen. Okay, wait. That is incorrect, really. Like, if you were on the AP test, if they asked, what do you need for hydrogen bonding? You said, I need hydrogen, you'd be incorrect. And that's what I try to get my AP students to remember, is it takes more than just hydrogen. It has to be hydrogen stuck directly to a nitrogen, an oxygen, or a fluorine to get hydrogen bonding. If it's stuck to any other element or it's just floating out free, that's not going to do hydrogen bonding. It can only be one of those 3 that it's stuck to. So if a hydrogen stuck to one of these highly electronegative elements, then it comes around something with a lone pair, maybe like another oxygen. I don't know what it's stuck to on each end. Just pretend it's stuck to something on each end. This hydrogen, which is going to very much have a partial positive charge, is going to be attracted to the electrons of that oxygen. Okay, so first off, the requirement: hydrogen stuck to a nitrogen, or hydrogen stuck to an oxygen, or hydrogen directly stuck to a fluorine. It has to be a direct bond, covalent bond there. Okay, it's going to be attracted then to something that's negative, that is like electrons, lone pairs that are going on. Okay, so that's hydrogen bonding. You know you have hydrogen bonding if your formula can have hydrogen with one of those 3 elements. It should hopefully be that easy. Water is a good hydrogen bonder because water is H2O, hydrogen and oxygen. It will bond well. Trying to think of something random. BH3. Not going to hydrogen bond because the H is not stuck to nitrogen, oxygen, or fluorine. Okay. Still in that same covalent bonding column, the second type of intermolecular force is dipole-dipole. I've already talked in pretty good detail earlier what a polar molecule is. That is where one end is like slightly negative. Let me get a dark color going on here. Okay, one end is negative, the other end is positive, and like little poles of a magnet, check it out. The positive is going to repel other positive polar molecules, but be attracted to the negative part. So there'd be an attraction there. And this negative would be attracted to a positive, and this positive would be attracted to a negative, and they all start lining themselves up like little magnets, all trying to hold each other together. That is dipole-dipole bonding. The idea is that we need a polar molecule, and it happens between 2 of them. That's why we call it dipole-dipole. Polar molecule is a dipole, has 2 poles. Okay, and so 2 molecules that have poles, dipole-dipole, is dipole bonding. Okay, it's also possible that the positive would be attracted to something negative of even, I don't know, a chloride ion. I don't know why a chloride ion would be just floating around in the middle of nowhere, but the positive and negative kind of part. Electrons are negative, so it would be attracted to that. So opposites attract. It's Coulomb's law still working out. Okay. Then the third type, so we're still in that covalent bonding column. The third type of intermolecular force are the London dispersion forces. London dispersion forces result from the constant movement of electrons. So catch this. What do you need for London dispersion forces? Wrong end. Electrons. Name one element that does not have electrons. You can't, because they all have electrons. Hydrogen has one, yes, that's not many. Iodine has a whole lot, because it's a big atom. Element 118, the biggest atom we have so far, would have 118 electrons, so it has a lot. But all of them, every element then, can do London dispersion forces. And yes, you can abbreviate that as LDFs. It is officially acceptable, even on the AP exam, to call them LDFs, London dispersion forces. So what happens is, like I get a polar molecule close to even a nonpolar molecule, well, that negative is going to repel the electrons kind of to the other side, and for a moment I'm going to have a bond going on there. But remember, electrons are always in motion. So it makes very much like a dipole-dipole bond. Okay, see how like the negative end of this molecule is attracted to the positive end of that molecule? It's very much like a dipole-dipole, but it is, we often refer to as instantaneous. Meaning, there one instant, gone the next, because these electrons are always moving around. So maybe the electrons line up just perfectly where they can attract each other in one moment, and then the next moment the electrons might move to the other side and repel. So London dispersion forces are noticeable. They are the weakest of the three types of intermolecular forces. They come from electrons. That's all the requirement you need. Hydrogen bonding, you need hydrogen and nitrogen, oxygen, or fluorine. Dipole-dipole, you need a polar molecule. Everything can do London dispersion forces. But London dispersion forces are super weak because they're temporary. They're there one moment and gone the next.
In any atom, the random motion of electrons around the nucleus can create a positive pole in one part of the atom and a negative pole in another part. If another atom is located nearby, the temporary dipole can induce a dipole in it as well.
So you notice they're saying dipole. That is like a dipole-dipole attraction, but it is weak because it's temporary. See, it's gone.
Electron motion causes the dipoles to disappear.
Okay, so again, it's noticeable. It is very much similar to a dipole-dipole force, but it's temporary because those electrons are always moving. They might line up perfectly great to stick together one moment, and then the next moment they've moved on and it's destroyed. So London dispersion forces, everything can do London dispersion forces because everything has has electrons, and even the more electrons an atom has, the greater the London dispersion forces can be, noticeably larger. It is very possible London dispersion forces in some elements could be stronger than hydrogen bonding in other elements. So don't discount London dispersion forces, but they're generally weak because they are temporary. They're instantaneous dipoles. Okay, so quiz time. I want you to try to figure out what kind of bonding is going to be going on. Of the three types of intermolecular forces, which is each of these going to be? Let's start with A. I see hydrogen stuck to fluorine. So can I do hydrogen bonding? Well, hydrogen stuck to fluorine, yes. Hydrogen's going to end up being the positive part, fluorine's going to end up being the negative part. Do I have an attraction there? Yes. So I would call this hydrogen bonding. Now, there would also be dipole-dipole bonding going on. There would also be London dispersion forces going on. But hydrogen bonding is going to be the strongest of the three choices in that situation. So we're going to just declare hydrogen bonding and move on. Why mention the weaker ones? Now look at B. It looks similar, but is it? Well, now it's fluorine to fluorine. So can I do hydrogen bonding? No, there's no hydrogen. Can I do dipole-dipole? Well, no, I can't because those aren't polar molecules. Those would be nonpolar. So what's left? London dispersion forces. That's the only thing left. But everything can do London dispersion forces, so that must be what's holding it together. Which is also one of the reasons that hydrogen fluoride is typically a liquid at room temperature and fluorine is typically a gas at room temperature. that stronger hydrogen bonding holds it together, and it takes more energy to turn it into a gas, more than room temperature can supply. What about over here? I have a positive there, and I have water. And water is, you just need to know this. You really by now should have picked up on this. Water is a polar molecule. It has that partial negative near the oxygen side, partial positive on the hydrogen end. And so I have a negative to a positive. That would be an ion to dipole kind of bond going on there. A sub-variation, a subset of dipole-dipole. Ion dipole bonding going on there. And I'd be okay if you called it dipole-dipole bonding, but it's technically ion dipole. But it works just like dipole-dipole. A positive is attracted to a negative. Okay, what's going on here with sulfur and oxygen? Well, can it do hydrogen bonding? No, it cannot. Okay, up here we could, but, well, okay. This part's set up for hydrogen bonding. That part was not. There's no hydrogen there. And so the hydrogen has to be on like both parts, just to let you know. But, okay, so can't do hydrogen bonding. Is this a polar molecule? Yes, this would be a polar molecule with the oxygen side being negative and the sulfur side being positive. How do I know that? Oxygen's more electronegative. Done. The electrons are with the more electronegative element. So that was wrong. That's supposed to be a negative side there, positive side there. So I have a positive side of a molecule being attracted to a negative side of a molecule. That would be dipole-dipole. Not hydrogen bonding because we don't have hydrogen. And it certainly does do London dispersion forces. All of these would do London dispersion forces. It's just not the strongest in each individual one. And so we like to talk about what the strongest force is for each individual one, because then it's a given all the other weaker ones are there. All right. Maybe. Okay. We are actually done with that covalent column. Now we're on the far, far right with the metallic bonding. There's one thing I want you to know about special topics for metallic bonding, and that's this thing called alloys. Alloys are mixtures of metals, or metals with nonmetals. Mostly metals, okay, but you can mix in a few nonmetals and get some new properties. Pretty cool. And the new mixture has new properties.
Remarkable strength come from. In metals like iron, the atoms are packed together like sheets of marbles. But when pushed or pulled, they can slip and slide past each other. But steel also contains carbon. The carbon atoms fit in between the iron atoms, limiting their freedom of movement and making it harder to pull them apart. Steelmakers long ago learned that by adding more carbon, you can increase the steel's tensile strength, but you give up flexibility, which is something that the arresting cable needs to wind and unwind. The trick is to find just the right balance.
Okay. So alloys are mixtures of metals, sometimes with nonmetals too, that give new properties. So iron will rust, but if we mix in some other metals and a few nonmetals, we get stainless steel. It's harder than iron and it resists rusting. That's why we call it stainless, because it doesn't rust nearly as easily. Now, I as a chemist, I can make it rust. I have no problem being able to do that. But under normal conditions, stainless steel does not rust. Regular iron is relatively soft. Like you build an axe out of iron, you go to chop down a tree, I bet about halfway through the tree you have to resharpen your axe of iron because the blade has gone dull because it's soft. Make an axe out of steel, iron with carbon in it, and now it's going to hold that cutting blade for a much, much longer time, which is why if you actually go to buy an axe, you'll find steel axe heads, and they'll even say nifty things like flame forged or something like that to get you to make it, make you think it's special and you should buy their axe as opposed to some other. But we get new properties. When we mix metals and some nonmetals to get a new mixture with new properties, there's two options. Okay, we can have two types of alloys: substitutional and interstitial. Okay, and I know interstitial is a pretty fun word to say, right? Substitutional interstitial. So you need to know there's two types of alloys when we mix metals and maybe some nonmetals in there. Substitutional, interstitial. Substitutional alloys occur when atoms of similar sizes replace each other. So it's all about size. If the elements you're working with have atoms of roughly the same size, they will make a substitutional alloy, like here. Maybe this was iron in the grayish color, and maybe this is copper. They're very similar in size on the periodic table, like the pure elements would be very similar in size, so it's no surprise they would like substitute one for the other. Okay, what is the alternative? Well, interstitial is the alternative. That's where you have atoms of noticeably different size, so much so that the smaller ones can stick in between the bigger ones. That's the inter part of interstitial, between. Okay, and it is actually possible to mix metals that are similar and different in sizes and get a combination of the two. But there's only two names for it, so we'd say substitutional or interstitial, or both substitutional and interstitial. So those are the options. It's all about size. This should be some easy points on your Canvas quizzes and on the test. Substitutional if they are similar sizes, interstitial if they are very different. Small will stick inside the big. And that's, I would give you the information for the sizes and you would just determine, oh, they're very different in size. That's interstitial. They're very similar in size. That's substitutional. Okay, we're actually done with that big super large T-chart. I would like to wrap up with some final review of the strengths of bonds, and that's what this page is about. I would recommend starting this on a brand new sheet of paper so you have room to write it down, and if you need more time than I'm going to give you on this video, then just pause it when you need to and write stuff down. But this is just a great review of everything we've talked about so far. When it comes to our intramolecular forces, the ones inside, because intra means inside, the strongest of all the types of bonding is actually one we have not talked about in these notes. That is the covalent network. Why have we not talked about them? Because there's like two places where they exist. They exist in diamond and they exist in quartz. And that's why diamond and quartz are like the hardest substances known to man, because they are the, and women too, I'm sure. They are covalent network. Every single atom in a diamond is bonded to every other atom. Like seriously. So an atom bond, 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 other atom bond, 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 other atom, and it just keeps going and going and bond 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 and bond. And so literally a diamond, if you think about it, is one giant molecule because every atom is somehow connected to every other atom, which is why they're very hard and which is why they take very careful techniques to cut them just right. Because with training, you can actually figure out by looking at a diamond carefully where you can separate these bonds and get the atoms to pull away from each other. And if you cut it just right, it also helps with the shininess of the diamond and showing off its clarity and these other things that people that like diamonds seem to talk about. I'm not big into diamonds, but there you go. What we did talk about was ionic. Ionic tends to be, in general, the strongest kind of intramolecular force because it's a gazillion positives and a gazillion negative ions stuck together. And you could imagine, I mean, two magnets stuck together, I can pretty much pull that apart, right? But if I had a gazillion magnets stuck together, I could hang from it. I could strap it to like the bar of a chin-up bar and just hang off of it, and it's not going to go anywhere. Okay. Molecular or covalent compounds, they tend to be generally weaker than ionic. And that's about all we can say. Generally weaker than ionic. Some are pretty strong. Some are not all that strong. And the metallic, it's really hard to put it in a chart because some metallic bond is super strong and other metallic bonds are not strong at all. So I just kind of threw it in here because for the most part, metallic bonding is a little bit weaker than the other two in general. It's a little bit easier to break apart a metal because those planes of atoms can like slide past each other when they're hit, sort of a thing. So you can like break off little pieces and layers and that sort of thing. Then and this is not drawn to scale at all, but way down at the bottom of strength, so up at the top was high strength. Way down at the bottom is our intermolecular forces. Of the three, hydrogen bonding is the strongest. What's it take to have hydrogen bonding? You need polar molecules with hydrogen stuck to nitrogen, oxygen, or fluorine. Okay. Now, if hydrogen is stuck to nitrogen, oxygen, fluorine, I guarantee it's polar, so it works out really well. But there you go. For dipole-dipole, all you need is a polar molecule. It's not as strong as hydrogen bonding, but it's still very noticeably there. And then London dispersion forces, all you need is electrons, so everything including non-polar molecules can do London dispersion forces. And so we would look at what's the molecule look like. Does it have hydrogen with NOF? Yes or no. If the answer is no, then you'd like cross that off your list. And does it have a polar look to it? Is one end going to be having a different electronegativity than the other end? If the answer is yes, then it does dipole-dipole. If the answer is no, you cross that off your list. And what about London forces? Well, everything, even nonpolar molecules, can do London dispersion forces. So it's always there. It's the comparatively weakest of the three. But with a lot of electrons, it can still be noticeably strong and have a noticeable effect on the characteristics of compounds. So it does exist. Don't ignore it. All right. So that is our Unit 7 notes all said and done. And we're going to be practicing this in class in several ways. We've got some labs going on. We've got some Canvas quizzes going on. Be sure you keep these notes handy. And as you use this information in class, again, I feel like a broken record saying this every unit, but as you use your notes in class, if you find something you wrote in your notes is lacking in what you need to remember, fix your notes. That's why you have until the day of the test to turn them in, so you have lots of days to fix it up and make them good notes that you can use for review and summary purposes to get ready for the test. All right, so that's going to be it for us for Unit 7. Good luck.